Yeah, good afternoon, everybody. I take this opportunity here to welcome everyone for this webinar. A great effort taken by Chennai chapter and the southern region for this to conduct this webinar. I would like to thank Dr. Saravanan sir for conducting this seminar here. So I request everybody to please take all the benefits from this seminar. Thank you very much.
Thank you, Chairman. Before starting the presentation, I will introduce Dr.V.S Saravanan to the forum. Good afternoon, Saravanan sir. Raman here.
Good afternoon, sir.
Good afternoon. So, Dr.V.S Saravanan, having professional summary, he accomplished in streamlining the production process, project planning, execution, and rich knowledge in cast iron metallurgy and product design, having industrial experience of 25 years, good in maintaining statutory and regulatory requirements of the organization, managing with consistent success and achieving results in terms of revenue, cost, quality, productivity, delivery, and other set goals. So he started his career in the year 1996-97 as engineer in Solvay Engineering Industry at Coimbatore, and grown up to the level of junior vice president at Indoshell Cast Pvt Ltd, Coimbatore. Total span of 25 years industry experience he is having now. His responsibilities is having widespread functions like engineering, quality control, quality engineering, and handling the total foundry operation for more than 10 years as general manager. On education part, he is BE Mechanical Engineering, passed out in the year of 1996 at Bharatiya University, and MBA in the year of 2000 at Bharatiya University, then ME Industrial Metallurgy at PSG College in the year 2010, and doctorate PhD in Metallurgical Engineering in 2017 at Anna University, Chennai. In addition to that, he has got more skill by obtaining many qualifications like Six Sigma Green Belt certification, a lead auditor of ISO standards of 14,001 and 45,001, and qualified internal auditor for IATF 16949 from TVNR. He has got his own achievements. He presented many papers, and he received Young Foundryman of the Year award from Institute of Indian Foundrymen for the year 2013. That is about 10 years back. And Distinguished Elements Award from Sri Krishna College of Technology in the year 2017. He presented many papers, totaling about 15 papers in national and international conferences, 26 papers published in national and international journals, and 11 papers in Indian Foundry Journal. 3 papers are published in Pakistan Foundry Journal, South African Foundry Journal, and European Trade Journal with the permission of Indian Foundry Journal. So coming to other information, so president of, so he is doing welfare and social activity also. Manizam Children Welfare Association is the president. The extended arm of self-association to help the education requirements of the destitute people in the company. Member in Indian Institute of Metal, Technical Committee member of Institute of Indian Foundrymen, Coimbatore Chapter, Environmental Committee and Executive Member of Coimbatore Sitco Industrial Estate Manufacturer Association, Member of Program Advisory Committee of Department of Foundry Technology, PSG College, and a member of Board of Program Advisory Committee of KPR Engineering, member of Board of Program Advisory Committee of SNS College of Engineering, and Management Committee member of SCE Engineering Chapter. He almost visited across the globe: USA, Germany, Italy, Czech Republic, France, Sweden, Norway, and Denmark. He has got the interest of learning and teaching and solidification science of metals. So there is no other leftover, sir. All the area you have covered. So now I request Dr. Saravanan sir to take the presentation thereon. Thank you, sir.
Thank you, sir. Thank you very much for your introduction. So now, are you able to see my screen now?
Yes, sir. Yes, sir.
No,
Yes, sir.
sir.
Yes, sir.
No.
Now it's come.
Okay, so good afternoon. So this is this session. We are going to learn something about the thermal analysis. So here, the thermal analysis. I'm going to talk more about this ductile iron castings because ductile iron is very sensitive. So this thermal analysis, how to use thermal analysis software and how to interpret the results towards ductile iron is very useful. Of course, it is actually applicable to gray iron also. So, but we'll see more about ductile iron, how to use this thermal analysis software for that. So, what is actually a thermal analysis? Um, so it is nothing but analyzing and predicting the solidification behavior of the metal through interpretation of shape and arrest points of cooling curve of the solidifying liquid metal. So this is a small definition. So here, again, there are some wordings, some solidification behavior and then cooling curve. So what is actually, what do you mean by the solidification behavior? So this cast iron, particularly this ductile iron is a very sensitive metal towards the process parameters. So sometimes we cannot predict the solidification of ductile iron. So sometimes, even though in the established process, all the castings, will come okay one time and we are getting 10%, 20% leakage. In another time, if you see the process parameters, everything may be okay. So we could not find out what is the exact reason for this shrinkage. And basically, if there is any shrinkage issue, we will analyze the gating system, risering system, increasing the riser, change the sleeve, something like that will do. So it is a real headache for engineering department. But what has created this shrinkage issue? It's very difficult to identify the reason, root cause, pinpoint the reason, because there are so many variables in ductile iron production, starting from the charge material to pouring, and even the cooling, the molding properties. So all those things actually playing a vital role. So here, identifying and pinpointing one particular root cause is very, very difficult sometimes. So how to work with this metal? So that is a real challenge for the foundryman. So for that, this thermal analysis software is actually it is giving a helping hand to some extent. I'm not saying that it is going to solve the entire problem, but it will help to some extent to come out of this issue. At least we can identify some areas to correct. So here, the solidification behavior, before that, the ductile iron is a very sensitive material, as I told earlier. So here, the solidification range of ductile iron is, it is actually a short freezing range. So, the thin skin is forming over the metal mold area. So actually during ductile iron solidification, the graphite precipitation is there. So it creates more amount of pressure. So maybe the experiment says it is nearly about 50 to 60 bar pressure during solidification. So at that time, if the skin is not thick, so all the pressure developed inside the molten metal will exerted on the mold wall. So then again the mold is not so strong, then it will try to dilate and then the volume of the metal will increase. So we will get some shrinkage issue and then bulging issue. So many things will happen. So here, more amount of the important thing is how to control the graphite precipitation, how to control the nucleation potential of the metal. So all those things actually it is a very important as far as cast iron is concerned. Here cast iron means both ductile iron and gray iron, and this ductile iron is more sensitive when compared to gray iron, because the gray iron is actually literally a long freezing zone, so it forms a thicker skin immediately. So the pressure exerted on the mold for the same time will be less when compared to gray iron, even though the pressure developed is almost same, but the pressure exerted on the mold is little bit less because the thicker skin actually absorbing the pressure little bit. So here the bulging related issue is less, shrinkage related issue is less. So how to overcome this issue, how to control these things. So what is creating this kind of solidification issues, nucleation issues. So for that, this thermal analysis software will give some answers. But I cannot say that if you implement this software, if you buy the software immediately you cannot come out of this problem. Okay, so it will actually give the idea, so where we can attack, where we can take the corrective action, so like that. So we have to work with this software, because this software again it will vary, the results will vary between foundry and foundry. So we have to closely work with the software, adjust the software according to our foundry process. So we have to, because the thermal analysis software is working based on the thermal arrests. So if you have what is thermal arrest means, so during the solidification, the course of solidification, so sometimes there is a sensible heat liberation, latent heat liberation takes place. So during the latent heat, only the phase transformation will take place, and then the temperature remains same for a while. So at that particular point is called actually the thermal arrest. Here, what we are talking about. So the cooling curve is nothing but the time versus temperature it shows. At that time, how the heat is liberating from the metal. So according to that, the curve shape will change. So based on the shape of the curve, actually we can interpret many things, and also the arrest points, the thermal arrest points. So where it is located and what is the relationship between the temperature. So we can study many things. It will give a lot of inputs. So by studying these inputs very closely over a period of time, maybe it will take a longer time, maybe 6 months or even 1 year. So we can actually come to the prediction point of view. We can predict something. So if the arrest point is like this, the difference between the two arrest point is like this, the metal will behave like that. So like that we can actually predict something. So for that we need to closely work with this software. So many foundries, initially by the bought this thermal analysis software, they put the metal into that cup, and it will show some reading. So the analysis shows it is good, but actually will get a problem. So immediately, we will lose faith of this particular software. So not like that. Actually, we have to work with the software, fine tune the software, adjust the slopes, all those things according to our metal, and then slowly we have to start our prediction. So here this is the thermal analysis, and the problems what we are facing the foundries. So we have almost all the foundries, we are having the spectrometer. So spectrometer, it will give all the chemical composition. Yes, of course, it is very important. So all this quality of the metal, and then the behavior, solidification behavior, mostly related to the chemical composition. So the carbon increases and silicon increases, the solidification pattern will change. So that is one thing. But apart from that, sometimes if all the chemical composition, everything will be as per the specification, but again we will have the problem. So what kind of problems sometimes? So metal holding due to power cuts. So it is unavoidable, metal holding due to power cuts. But it will affect the quality of the metal. So how to improve the quality of the metal to some, because we cannot actually, once the metal is deteriorated, we cannot bring back to the original, but we can improve to some extent. So here the metal holding due to power cut, it is unavoidable. Sometimes metal holding because of some other reasons. Maybe molds may not be ready at the time of metal ready, and then maybe some breakdowns. Maybe operator not available at the time of metal readiness, or at the time, so they will search for persons inside. Sometimes it will happen during the night shift. So here these kind of delays will happen. So this will actually deteriorate the metal quality. So sometimes, the chemical composition correction also delays the metal preparation. So we want to correct the metal as per the chemical composition, as per the requirement. So for that we need to add some alloying elements, correct the metal, again do the spectro result. So this will actually take some time. So and then superheating of the metal. So actually it is very, very important thing. So we should not superheat the metal because it will actually kill the nucleation potential. So the superheat of the metal, sometimes we don't know whether we are superheating the metal or not. So maybe the 1500 may be the optimum temperature, but the temperature will go up to 1530. So we don't know whether the metal has reached 1530 or not. So once if we measure the temperature, then only we come to know that the temperature reaches 530. So again we will reduce the temperature to 5500, and then we will start pouring or start treating the metal. So but the reaching of 1530 is actually killed the nucleation potential. So reached is reached. So how to control and how it has affected the nucleation potential. So this is one area. So and then inconsistency of quality scrap. So actually we are buying scrap from different sources. So we do not know the quality, because even though we are checking the chemical composition, that will give only the important elements. Sometimes maybe 20 elements, 25 elements. Apart from that, there are many things are there. Even the recycling, how many times the scrap actually undergone for the recycling, that we don't know. So these things again, it will affect the quality of the metal. And then we'll put sometimes rusty scrap also. So normally, short blaster scraps we are putting, if the runner risers, all those things. Sometimes if it is in CRC scrap or something like that, rusty scrap, we don't know. We have to put as it is, and then the scraps will have not only rust, sometimes it have some coatings also. So once if we put the scraps inside the metal, then only we come to know that there are some coating because of the fumes and then different color flares, all those things. And then poor melting practice. So from the charging sequence, how to melt. So we should not do very fast melt rating, all those things. So charging sequence, that is also important. So how to add the charge material, where to add the carbon, silicon, all those things, that is also very important. And the inoculation practice, how we are doing inoculation practice. So these things actually decide the quality of the metal. So these things actually will not reveal in our spectro analysis. Spectrometer tells only the chemical composition. So here these things actually we can find out these things to some extent with the thermal analysis software. So all these inconsistencies will give these results. So inconsistent quality of castings, increasing scrap percentage, increasing throughput time, delays in deliveries, increasing the manufacturing cost, these things. Chemical composition analysis does not expose the following inconsistency, that is poor quality of charged material, prolonged melting duration, superheating, presence of excess oxygen, nucleation potential, so gravitation potential, all those things, it will not come in spectroanalysis. So this will, we can get all these things, the answer from the thermal analysis software. So now what is thermal analysis software? Actually, this is a little bit like a CE meter. So we are using a pouring cup. So we are pouring the metal into that, and then there is a small thermocouple inside. So the thermocouple actually it will create actually what this millivolt, it will generate millivolt. So, and then this millivolt is actually we are taking into we are converting into digital thing, and then we are taking into the software, and the software actually it will give the plot the cooling curve. So according to the millivolt generation. So for each millivolt, they have the standard temperature. So based on that, they will actually plot the curve. So the shape of the curve, how it is, and then what is the time taken for that, where are the arrest points come. So based on that, the software will get a lot of inputs for us. So by studying these inputs, actually we can predict, we can tell the nucleation potential of the metal little bit. So this is actually the thermal. This is the thermocouple. So there are two types of thermocouple at this cup. One is the plain and one is the tellurium coated cup. So once if we want to check the base metal analysis, we have to use the tellurium coated cup. So once if we pour the metal, immediately it will cool because of the tellurium. So it forces the cooling, and then we can get the base metal things. So the concept is the heat generated inside the thermocouple. The thermocouple actually produce the millivolt, and then by digital processing unit, it converts the millivolt into a temperature scale, and then it is plotting the cooling curve. So this is actually the general cooling curve. So this is for the pure metal. So for pure metal, we can only the 1 point melting point, and then the freezing point, both are same for the pure metal.
Sir. You answer.
Please, please, participants, please mute yourself. Participants, please mute yourself. It is disturbing the presenter.
Okay.
Okay,
Okay,
sir.
thank you. Okay, thank you. So here, you can see the melting point and then the freezing point for the pure metal is same. But in our case, it is not a pure metal, so we are adding so many alloying elements. But above this melting point, this particular uh, heat, what amount of heat we are giving to the metal, that is nothing but superheat. So how much we need to give the superheat, that actually superheating the metal, that decides our the pouring methodology, what is our treatment weight, and what is the time taken for pouring. So all those things actually it is very important to decide how much temperature we can go above this melting point. So, so as per this, 1140 is the eustatic point. There we are getting all the solidification actually started in the metal in our cast iron. But above which, what can be the maximum temperature we can go? So theoretically, 1140 plus 200 degrees centigrade, the excess met and plus 80 degree, maybe 1300, 1400 degree is sufficient. Okay, but because of the pouring constraints, we are actually heating the metal up to 1500 degree. Even sometimes some foundries, having very small pouring weight, more number of molds, they are going up to even 1550, 560, even for the cast iron. So whenever if you are going for superheating, then actually we are killing the nucleation potential. So we need to work on how to reduce the pouring time. So instead of increasing the temperature to adjust our pouring process, instead of that, so we have to uh, improve our or reduce our pouring time. So that is very important. So I will just skip here. So you can see this is actually the 4.3 eustatic, and this is 1140. This is the eustatic temperature, and this is the eustatic composition. So the thermal analysis and all those things is derived actually all those things derived based on this um, carbon equilibrium diagram. So now, before going into the thermal analysis software, and just the solidification, how it is happening inside the metal, what are the phases. So actually once the metal is ready in the liquid metal, then in the course of time there are more nuclei will form like this. Okay, so the nuclei, if it is forming nuclei, then actually it loses, the metal is slowly loses its the kinetic energy, because the more amount of elements inside the metal, it is moving very fast. When the temperature is increases, the movement is very speed. So once the temperature is going down and down, the kinetic energy in between that elements, it is actually slowing down, and then it is coming close together, and then it is binding each other, because they have studied more things in our schools and colleges, the ionic bond, covalent bond, so many things, So the ion, whenever the atoms come close to each other, then it will bind each other, and then it is creating the solid phase. So here, more amount of nucleus will form, and then the slowly the nuclei will group together, and then it will grow as a dendrite. So the dendrite will grow, and then finally it will become a solid, and then we can see the grain boundaries also. So here our point of thing is the nucleation start, where it has start, at what temperature, and how many nuclei, how much of nuclei is actually created inside the metal, whether it is sufficient to continue for the further solidification process. So these things are very important. Sometimes the metal takes more time for getting the nucleation. Then there are some problems in getting the quality, that is a shrinkage or porosity, all those things will come. So here actually once if you pour the metal, for example, if you pour the cup inside the metal, that this pouring temperature, and you can see the arrest points. So already I told you the arrest points, I think, but it is actually the constant temperature at that particular point. There is only a phase change, there is no change in temperature. So in the cooling curve, it will show only the arrest point, arrest, like this. But if you enlarge it particular time, if it is possible, because normally the cooling curve software we cannot zoom it, but at that particular point, if you are able to zoom that particular point, you can see a small straight line, because there is a phase change only, there is no temperature increase, like once if you boiling the water, so at the time it reaches 100 degrees centigrade, the boiling point, then the temperature remains constant, and only the water actually it becomes steam. So like that only there only the phase changes happening. So like that here a small phase change happens, because the metal will become a small solid phase. So there the temperature remains same, but again it is not actually this particular point, the pre-request arrest point. It is not a permanent one, So once the small amount of nuclei is formed everywhere, so the temperature, the latent heat liberation will takes place, and then again the temperature of the metal will go up a little bit, and then again it will dissolve. Or otherwise, what happened? This arrest point, this pre-liquidus, even without the temperature increase, because of the latent heat, that existing temperature is just sufficient to dissolve the nuclei. So the nuclei formed here will dissolve. So that is called here. This is not a permanent one. This particular pre-liquidus arrest point. So this is called actually the pre-liquidus arrest. So here what happens, once the nuclei formed again, it will dissolve this on this particular point. So what it shows actually, this pre-liquidus arrest point, it shows excess of oxygen sometimes, the source of oxygen where it comes. So it actually comes from the rusty melting scrap, furnace lining, coatings, so moisture somewhere. So if the excess amount of oxygen is there, so the metal, the cooling curve will show this small liquidus, pre-liquidus arrest point. So sometimes if we have the pre-liquidus arrest point, so it shows the more amount of oxygen, so we have to remove the oxygen by adding deoxidizers. So this is one important thing. So if excess oxygen is not desirable, So if there is an excess oxygen, maybe 100 ppm or something like that, then it will create issues like it will take more amount of magnesium during magnesium treatment. So, so this magnesium oxide inclusions will come, magnesium pickup will not be there. Maybe the nodularity percentage will come down. So sometimes the gas defects, micro gas porosities inside the metal. So these things will be there. So we have to carefully arrest this, remove this liquidus arrest so that the scrap, all those things we need to take care. And then again the temperature is coming down, then again one more arrest point will come. So this particular point is called liquidus arrest. So TL, sometimes TAL, whatever it may be. So this is actually this is actually a permanent nucleation site, because the temperature drop this particular point is really sufficient to stabilize the nuclei, because after that once the nuclei formed, the kinetic and larger losses, then this particular temperature cannot actually split the nuclei and these atoms again. So it comes close together, and then again it will become a stable. So the heat in the metal at this particular point is not sufficient to dissolve this nuclei again. So this is actually the permanent one. So here I know once this nuclei form, then again all the nuclei atoms comes close together and it will form a big nucleation site. So here this is actually the critical radius and all those things. So once the critical radius formed, then it will become a stable. Up to this, for example, this is the critical diameter, then if it is the smaller diameter, if it forms again, it will dissolve. But at this point, this become a stable nuclei. So this is called TAL. So what happens here, the first nucleation sites actually it is forming and then starts growing slowly. So here there are two type of things. One is hypereutectic and hypoeutectic. So hypereutectic means first, the first solid may be graphite. Hypo means the first solid may be austenite. So austenite tends to precipitate and then it will start slowly growing. So this is TL. So this particular point may be liquidus point here, and then it is growing slowly. This is also the dendrites going in all 360 degrees direction, and then it is growing. So the early liquidus arrest promotes the possibility of forming surface screen, because early liquidus arrest means the more amount of austenite will form. So then there are chances of getting surface shrinkage defects. So how to so bring down these things, actually we will see it later. So this liquidus temperature actually derived from the carbon equivalent. So that is there is a in the software actually they have a lot of formulas. So based on the temperature and then the carbon at that particular time, actually they are actually creating these arrest points from that. So from this arrest point again we can calculate the carbon equivalent also, vice versa. So this will form between 1125 to 1150. So and then the early liquidus temperature indicates low carbon equivalent, and then the presence of insufficient active carbon, because at that time the first austenite actually started growing. So here once the hypereutectic, first graphite starts precipitating at this particular point. So 80% of the graphite actually started precipitated between TL and TER. So TER, what is TER? I will tell you later. And then the remaining 20% will form TER and T solid. So T solid means after completion of the solidification. So what is how much graphite precipitating between TL and TER? How much it is precipitating between TER and T sol? These things actually determines the quality of the casting. So these are all the indications with the TL. The high TL value indicates low carbon equivalent, and very low TL indicates high carbon equivalent. So there is a chance of graphite flotation also. Sometimes if the graphite addition is not correct, or that will again it will shows the very low TL values. So here, so desirable range for this TL before magnesium treatment is this much. So from that 1001 to 1128, and then from that, they are actually calculating the CEL. So CEL means carbon equivalent liquidus. So 4.32, and then this is for this, for each temperature they are having different CEL values. So like that, for this the treatment between 1128 and 1149. So it is a desirable range. So after TL, then again, it comes TES. TES means actually eutectic start. Eutectic means, so from that iron carbon diagram, we can understand that at that particular point, two solid phases actually starts precipitating from the liquid. So already, this particular point, so if it is hypoeutectic, arsenide precipitate starts, so then, here, this particular point, graphite will start precipitates. So graphite will start precipitating like this. So in between the so arsenite, so actually it is coming like this. So this particular point, two solid phases will start precipitating. One is arsenite and then one is graphite. Two solid phases. So like this, the graphite, the arsenite will start growing like this in dendrites, and then in between the dendrites, graphite will start precipitating and it will come down inside. It will settle inside the nucleation. This is dendrites. So this is actually the nucleation arsenite cell. So again, once the graphite start precipitating, again the arsenite will form over this graphite also, like this. So one side it is growing like this, and the another side over the graphite it is forming like this. So all areas actually it starts precipitating. So this is actually the hypoeutectic. So liquidus. So liquid, from that, the arsenite precipitates, and then the graphite coming, it is TES. So that is hypoeutectic, and then eutectic, first at that particular point both arsenite and graphite simultaneously it will precipitate. So that is eutectic point. So hypereutectic means first the graphite will start precipitate and then arsenite will start precipitating. So these are all the things. It will actually, this particular thing happens at TES. And then TEU, so that is the undercooling. So here, almost both the things starts the 80% what I told, so it is actually 80-70% of graphite and arsenite actually it is precipitated here. So TEU. So here, the difference between TL, TES, TU, these actually very important. So what is the gap between that? What is the temperature difference between TL, TES and TEU? If it is very close together, then the metal actually it is good. So if it is there is a temperature difference and then the TUU is taking very long time, so then there is a chances of getting shrinkage or carbide, all those things.
Okay.
So you can see the graphites inside the in between the
Because
arsenite
he
things.
was asking about this one gauge
Sir,
status. When I
sir,
checked with
participants, please mute
when I
yourself.
checked with our Saravanan, he was telling where is the AOI to start. So once again, we are.
Sir, excuse me. Sir, please participate yourself. Mute yourself, all the participants.
Okay, thank you. So here, some of the elements, so here the
Doctor, your voice is disconnected. Saravanan sir, not able to hear you.
yeah, so I think you have put the mute on me also.
No.
So now is it okay?
Sorry, now it's okay. Now it's okay.
Okay. So
Thank you.
here, while we are talking about TEU, so the TEU should fall between this graphite eutectic line and then carbon line. So here, actually these things actually in the software, they put all these formulas and then based on that only they are giving the prediction. So here, if the the solidification starts below the carbide eutectic line, then iron carbide eutectic will form. So here this is the carbide eutectic line. So this is TEU. So if the solidification actually, if it goes below this, then there are chances of getting carbides here, and then even sometimes there are chances of getting porosity also, because the nucleation potential is not good. So if the undercooling TEU temperature falls below the carbide eutectic line, then chances of getting shrinkage also here. So after magnesium treatment, inoculation, TL, TES, TEO are expected to come to the same values. Not same value means very small difference between these temperatures. So because the temperature difference, if it is more than TES and TEU is more, then the nucleation potential may not be good, and then we need to add more amount of inoculation. So like that. So here after that, after TEU, so here, as I said earlier, all the graphite actually precipitated here. So because of during graphite, the latent heat precipitation takes place because it liberate more amount of heat. So inside the metal, there are millions of nuclei or millions of graphites actually precipitated. So because the overall metal temperature will go up slightly, so that is why actually the curve is going slightly little bit up. So this temperature, how much it is going. So that is actually very important. So that particular point, that is called the temperature between after reaching certain temperature, then again will be stabilized. So that particular point, and what is the temperature, that is TEE. So that difference is called recalescence. So here, what amount of recalescence is acceptable? So maybe 6 degrees, 7 degrees is okay. So if the recalescence is more, so again what it shows, actually the temperature, if comes down like this, then the recalescence temperature will go up. Then it shows again the nucleation potential. It is not good. So that indicates this. And then how to improve the nucleation potential. So based on these recalescence, we can adjust the inoculation quantity, how much we are adding nuclear, because many foundries, they are adding a limit, that is a constant percentage of nucleation, maybe 0.3% or 0.2 percentage for gray iron and 0.4% for ductile iron, like this. Invariably, so it is almost constant for all the things. But with the using of thermal analysis very actively, we can adjust the inoculation also a little bit, because already if the metal is having very good amount of nucleation potential, sometimes no need to add more amount of inoculation, so we can reduce the inoculation percentage. Okay, so for that, these all these calculations, everything is based on this recalescence. So this recalescence is actually the maximum eutectic, the temperature, and then the minimum eutectic temperature, like that, the recalescence. So normally, if the recalescence is above 7 degrees centigrade, then the inoculated iron less than 4 degrees. So up to 6 degrees we can be okay. So it is okay. But if again it is more than that, then there is a problem. So after recalescence, the metal will become stable, that metal temperature. Why? Because that is the temperature, continuously it is dropping when the time is going up. So because the heat liberation here and then the temperature dropping, actually it is equal almost. So it becomes a stable at this particular time. So there is a straight line here. The cooling curve will show a straight line. And again, what is the length of the straight line? So sometimes, some software will show the length of the straight line. Some software will show the area between this particular point. So for example, the T solidus. So T solidus means there is a complete solidification of the iron metal. So here, what is the area between the TER and T solidus? Based on that, they can predict the solidification behavior of the metal. So I told particularly this T solidus is the so complete solidification of the iron metal. So here what happens in this particular temperature, many low melting alloys are there. So maybe copper is also a little less melting temperature than iron, chromium, moly, or tin, whatever it may be. So those things actually, those elements actually may be in liquid form at this particular point. So that is why I told this particular point is it shows the complete solidification of the iron metal. So some of the elements, low melting alloys, still in the liquid form. So again, it will start solidifying further if the temperature goes down. So actually here, this is end of freezing. So in this particular point, so complete metal, so including iron and other low melting alloys, everything becomes solid. So then here, what is the temperature difference between T solidus and T, and that is end of freezing. So if end of freezing is more, then it will actually, it says that we are adding more amount of low melting alloys. Like sometimes we are adding more amount of manganese, chromium, and then tin, copper, so many things. So that actually, sometimes it will deteriorate the metal, because these low melting alloys will actually solidify late, and then actually it is going towards the grain boundaries, and then it will settle at the grain boundaries in the carbide form, maybe vanadium carbide, chromium carbide, titanium carbide, whatever it may be. Maybe the amount may be very less, but actually it settled at its carbide, metal carbide. So then the grain boundary will become very weak. So then that will not get tensile strength, even though if you are adding more amount of manganese, tin, copper, whatever it may be, we cannot get the tensile strength as desired. So that is because of the enrichment of the alloying elements at this particular grain boundaries. And again, because the solidification takes place at the grain boundaries of these low melting alloys, again, the contraction will happen, and then these low melting alloys, again it will have small amount of micro porosities there. So very small micro porosities at the grain boundaries. So this actually again reduces the tensile strength of the metal. So we should be very careful in adding the low melting alloys. Mostly, we have to adjust, and then our the quality, adjust the metal to achieve the mechanical properties by adjusting the carbon and silicon. So that is very important here. So here, the tender freezing and T solidus, the difference is, when the difference is more than 50 degrees centigrade, then there is a possibility of getting micro shrinkage, because it shows more amount of micro, that is a low melting alloy segregated at the grain boundaries, and then chances of micro porosities. So that is actually end of freezing. So here what I told, so here there is the length, how much the length it is traveling, and then how it is flat. So it decides. So the curve, it shows how much the early graphite precipitates and what is the late graphite precipitates, all those things. So early graphite precipitation is more hypereuptotic. Then you can see the graphite size little bit more in that in the metal. So here also, so it is actually the hypereuptotic early graphite precipitation. You can see the graphites little bit on the bigger side, and this is euptotic. Means it is almost uniform graphite size. So like that, from the graphite also we can see which is the hypereuptotic metal, which is euptotic metal, and the thermal analysis curve actually it shows that particular things. So here one more thing is this is actually the graphite euptotic temperature, and this is actually the carbide temperature. So actually they derived this particular line. Actually it is a virtual line, actually virtual boundary. So this is actually the formula they are having in that. So in this boundary we need to have this TEU and TER, all those things. So if it exceeds here like this, then there is a problem. So some of the elements, actually it pushes the grain, this boundaries, graphite euptotic temperature line and carbide euptotic temperature line. So here what happens, the chromium, vanadium, titanium, actually it is actually pushing towards each other. Then it is narrowing down. So narrow down means then automatically the TA will go down. So these things, it is not desirable. That is addition of chromium, vanadium, titanium. If the metal is, the content in the content of the elements in the metal, it is more, then we will have the problem in the metal. And these things, the silicon, nickel, copper, cobalt, aluminum, these things actually the widen the range. So it is good, because if it is widened, then automatically TU will come inside. So actually they are telling it is good. And some of the elements, it is actually pushing both the lines simultaneously. Manganese, moly, vanadium, phosphorus. It is also not good. So the first not good is this chromium, vanadium, titanium. Second not good is good, and this is good. So according to that, these elements actually pushing these grain, these boundaries, and then it actually the solidification potential. These things actually varying according to the elements present in that, and then based on that we are getting all the microstructure, mechanical properties, all those things. So how where the TUU present, where it presents, and then what is the this boundaries. So based on that, actually all the properties of the metal has been derived, and the software is telling all those things. So here the inoculation addition, as I told you earlier, so we can adjust the inoculation percentage based on the recalescence. So for example, the inoculation required is the measured recalescence minus target recalescence divided by inoculation factor. So the inoculation factor is weight of the inoculant added divided by delta R. So delta R is nothing but the inoculation, that is a recalescence before inoculation and the recalescence after inoculation. So for that, we have to take minimum of 10 to 15 trials at least, to fix the inoculation factor. That is very important. With more number of trials will give more accurate inoculation factor. So based on that, we can predict. For example, here, assuming that our this recalescence before and after, that is the delta R, 5 degrees, what we are having is. And inoculation, what we have added is 200 grams, assuming that. So it is about 0.4 percentage for 50 kg ladle. So here. So then inoculation factor is 200 grams divided by this delta R. So that means 400 grams per degree C. So per degree C, that 400 to adjust per degree temperature per degree C, we need 400 grams of inoculation. That is about 0.08 percentage per degree centigrade. So to get the desired recalescence. So assuming that if I want, if the obtained recalescence is 8 in one particular heat, and then our target is 4. So I want to reduce 4 degrees. So 8 minus 4 into this inoculation factor. So then 160 grams is required. So this is the one we can calculate based on the recalescence and then inoculation factor. So we can adjust the inoculation factor, and we can adjust the inoculation quantity dynamically according to the inoculation delta R, that is R recalescence. If already the recalescence is very good and less, then we can reduce the um, inoculant. So you can see the graphite difference between, so this is uninoculant. I think it is uninoculant and this is inoculant. So here you can see a fair degree of curve with a good straight line. So this straight line actually indicates good amount of late graphite precipitation. So that is very, very important. Late graphite precipitation is very important. So at the time, metal is almost in semi-solid condition. So there, the graphite precipitation will take place. So here, the solid diffusion of graphite will take place here. So because of that solid diffusion, actually it pushes the metal, because the graphite density is less, but it occupies more space. So actually it pushes the metal. So at this time the metal is in semi-solid condition. So because of the pressure developed inside, so it is about 50 bar pressure inside. So the graphite precipitation, the force can push the metal a little bit. So at that time, even a small voids inside the metal can disappear. So that is why the late gravity precipitation is very important here. So these are all some of the examples I'm just putting here. So you can see here. So actually this is the carbohydratic line. So sometimes if the TEU going down instead of here it is going down like this, then we will get problems related to carbide. Sometimes it shows the nucleation is also not good. So it actually takes more time to create nucleation sites. So then again we are getting some porosity related issues also. And then here actually the graphite eutectic line is here, and then T solid it is here, and then end of freezing is here. Then this particular region, if it is very close, then it is good. So again if it increases here end of freezing, if it is more than 50 degrees, then what happens, the low melting alloys segregation and grain boundaries are more, then we will get grain boundary carbides. So this particular area actually they are calculating indirectly in the software, and they are predicting, they are giving the possibilities of getting grain boundary carbides like that. And then in some of the softwares they are talking about the velocity of solid phase, that is the velocity phase angle, something like that. So this actually this kind of angle, so they are they are telling about BPS angle. So it will what is the angle between that, that is 25 to 45 degrees the desirable thing. So based on that we can adjust the magnesium content also, magnesium what we are adding inside the metal. So they are adjusting the magnesium also. Sometimes we are adding more magnesium, so that is also not good. So if we add more magnesium, so the nodularity point of view it is good, but again it will create lot of issues like shrinkage porosities. If we add more magnesium, it actually promotes the shrinkage. So then magnesium related oxides, sulfides, all these defects will come. So we can actually limit the magnesium always to the maximum extent, so minimum extent. So that is very important. So for that, some softwares have the provision of measuring these angles, and then we will limit the magnesium content also. So this is what the solidification range, what I have discussed earlier. This shows the late graphite precipitation. So some of the software, it will it gives the area. So S1, S2, S3. According to this, that is predicting something, the possibility of getting the porosities, everything. So here, for example, if the S1 is more, so because the TL and TE low is, the area is more, then what happens, actually it shows more amount of austenite precipitation. So more amount of austenite precipitation means it is nothing but pure iron precipitation is more. Then there is a chance of getting porosity. That is this surface shrinkage also. So the area, from this area we can predict this thing, and the software will give all the inputs for us to adjust the metal quality. So like this, studying the cooling curve. So studying the cooling curve, actually we can predict a lot of things from the software, and then we can solve the discrepancy in the metal. So before pouring into the metal. So I'm not saying that we cannot eliminate complete discrepancy of the metal, but we can reduce some discrepancies. We can improve the quality of the metal, and continuously we are working with the thermal analysis software and fix the software parameters, all those things according to our process nature. Then we can the reliability of this particular software will be more. So like that, we need to work with the software. We have to adjust the slope in that particular thing. So the TL values, the T solidus, all those things, with the help of these formulas, what they have inbuilt in the software, we can slightly adjust the slope, and then we can improve the values. So then the prediction will become a good reliability for that. So like that, this thermal analysis software will help in improving our metal quality and then reduce our scrap rates. So this is about the thermal analysis software. Thank you. So if you have any questions, we can discuss now.
Gentlemen, you can raise your questions now. Yeah, Tulsi Raman, you can raise.
Sir, one doubt. How much percentage of inoculant recommended for this ductile iron, sir?
Sir, actually that depends on your metal quality and melting process and what kind of casting you are pouring. So normally for ductile iron, 0.4 percentage people are using. So according to your process nature, melting process, and then what kind of castings you are pouring, maybe thick casting or thin casting. So we can adjust the inoculation according to that.
No, for example, you tell me that thin castings, how much recommended minimum percentage of inoculant?
But that's what ductile iron 0.4 percentage average normally people are using.
0.4 average.
Yeah, 0.4.
Any further questions?
Sir, from Ashok.
Your voice is breaking.
Rupesh from Ashok Leyland Foundry Division.
Yeah, Bhupesh, you can ask.
Sir, actually, what is the recommended magnesium level we can maintain? Maximum level we can maintain for 500/7 grade, sir. Residual magnesium.
Bhupesh, how are you?
Fine, sir. Fine, sir. Fine, doctor.
So I'm very happy to know that you are asking now doubts in metallurgy. Okay. So actually the magnesium level, it's not depends on the material grade, So even 500/7, 600/3, whatever it may be. So the advisable magnesium level, the maximum is O5 percentage residual magnesium. Okay, so if your process allows to control the magnesium level O5, that is well and good. So if it exceeds, what happen again, it will actually induce the possibility of getting shrinkage velocity, carbides, and then magnesium related defects, magnesium oxide, magnesium sulfide, magnesium silicate, all those things. So actually, if it is possible to contain your magnesium with O5 percentage residual, then it is well and good.
Sir, minimum range of that magnesium, sir?
Hello.
Yes,
Yeah,
sir. Sir, what
repeat
is
the
the
question.
minimum range, sir? Residual magnesium.
Minimum range for
How much
what?
residual magnesium?
Sir, that's the minimum actually depends on the casting section thickness. So sometimes even if your magnesium is 0.017 or O2, that will also give a good nodularity. If the casting thickness is more than 017, O2, again you will get a flake graphite. It may not be sufficient. And also, what is your pouring temperature? So if the pouring temperature is more, then automatically O2 will not suffice. So the minimum, if the casting section thickness is less, even O2 percentage magnesium residual, that is also give you good nodularity.
Any more questions people want to ask?
Hello, sir. Hello.
Yeah, sir. Yes, sir. You can talk.
Sir, cup temperature, how much we can maintain? Cup temperature.
So which temperature?
We are using the cup. The cup delta cup temperature.
The tapping temperature we are maintaining 1550, sir.
No, tapping temperature is okay, but we are pouring the cup, no, the delta.
That is 1410,
Ah,
1400 to 1410, sir.
1400 to
1410.
okay. Okay, sir.
Sir, one more question, sir.
Yeah, you can ask. Please ask.
Yes, sir. I am from Southern Life Foundry Quality Assurance. What is the least sulfur percentage in the final composition? If the least percentage exceeds, that means beyond the least percentage, what happened to the quality of the SGN?
Sir, at least for sulfur, for ductile iron, The sulfur, if it exceeds more, that is also a problem. If it is very less, that is also a problem. So 0.08% at least we need sulfur. So if it exceeds, then we'll have all related that is the nodularity related issues will come. If it is very less, then again the same issues will come. So at least the minimum 0.08 sulfur, the base metal is required.
After final composition, so we are the result shows 0.006 and 0.05 like that, sir.
Yeah.
We are getting a good separation now. But theoretically, minimum you recommended 0.08 should be maintained.
Yeah. 0.08 is normally it is advisable. If you are getting good nodularity with 0.06, that is good. If you check, please, you are adding more magnesium or not, or otherwise some other parameter. If your nucleation potential in the base metal, if it is good, then I think it will work.
So we are achieving from base metal itself, sir. Then one more question, sir. At which point residual magnesium to be measured as the optimum of 0.05% maximum? At which point, sir? We are measuring at before covering. We are sample drawn to measure the magnesium. That means final composition only, sir. If end of the melt, the result shows more magnesium, residual magnesium, sir. At which point we consider for 0.05%.
0.5 is the residual magnesium in the last poured ladle.
Doctor, you are muted again, I think.
Hello.
Now it is okay.
Sir, voice broken, sir.
You are not able to hear the answer, Ravi Shankar?
Yes, sir. Now I am
Doctor,
here.
can you repeat the answer again?
No, the
yes,
0.5%, the residual magnesium, what we are talking about, the 0.5 is the last poured metal.
Okay, any other questions? Countrymen, please, gentlemen, you can ask the questions if it is required. Otherwise, we can close the session by saying vote of thanks. Anyway, thank you very much, Doctor, for giving this wonderful presentation to all the foundrymen.
Thank you, sir.
Really, the significance of thermal analysis we understood fully by going through your presentation. It was very well done. It was very benefit to the people who are all practicing the metallurgy. So now I request our Southern Region Secretary, Mr. Palani Murugan, to give the vote of thanks. Palani, are you in line?
Yeah, good evening, sir.
Yeah, you can
evening,
propose
sir.
the vote of thanks.
Yeah, good evening, doctor.
Good evening, sir.
How are you, doctor?
Doing good, sir. Doing good.
Yeah, anyhow, I did not want to disturb you that is why I did not say this thing. Anyhow, thank you very much for your nice presentation. So we would like to thank Dr.V.S Saravanan, Junior Vice President, Indoshell Cast, for having a knowledgeable session on the thermal analysis for ductile iron. We hope, I think, people would have gained a lot of knowledge about this thing. Anyhow, thanks once again, Dr. Saravanan. We also thank all the participants from all the chapters of Southern Region for actively participating in this knowledgeable session. So, Southern Region and with other chapters, we are going to conduct a lot of such like technical sessions in the days to come. We request all the foundrymen to request you to join and gain the knowledge about the technical these things. Thank you once again for all the participants, and thank you once again, Dr. V.S. Saravanan, sir.
Thank you, sir. Thank you.
Thank you, doctor.
Thank you. Thank you, Palani. Thank you.
Thank you very much. Thank you. Thank you, Chairman.
Thank you.